Okay, good. I think my microphone is unmuted now. Good morning, everyone. I'm using a new setup and it's not working super well. Can you hear me well?
Yes.
Okay, and do you see my screen? Wonderful. So with that, we will continue our discussion of mass spectrometry. So our today's topic is quantitation in mass spectrometry. A topic which is not trivial. So, and before we get to that, I want to finish our discussion of the use of triple quadruple instruments to achieve very high selectivity in detection of analytes without the need for high resolution. So as you recall, I had this slide. So the idea here is, I'm sorry, did somebody say something? Okay, I think it was just a feedback. So in this case, we're not looking at a particular ion. Instead, we're looking at the reaction that takes place in the gas phase. And this is exactly what allows us to achieve this unprecedented level of resolution, of selectivity rather. And I think based on your reactions that I've seen on the screen last time, quite a few listeners were interested in this story behind the example that I was going to use. This is the Major League Baseball scandal that took place, I think it was almost 2 decades ago, if not more. So, and interestingly, the people who eventually went to jail as a result of that, they served their time, but they didn't change their habits. And so this screenshot that I'm showing here, so this is the new business adventure of the person, of the chemist who was at the center of this scandal. So he is again in the business of making and selling anabolics, although now he is branding them as natural or green, so they're not even anabolics in the advertisements. But one thing that was particularly hilarious to me was well, you can look at the structure and decide for yourself if this is an anabolic or not, if this is steroid, a hormone. I think it is. But these are the engineered feedbacks that are left on the sites that sell these products. So I intentionally removed the name of the person, right, to make it anonymized and impersonal. But I thought this part of the feedback, he is yet to fail the consumers, was particularly hilarious. For those of us who know the history and what happened 10 years prior to that, in terms of the Major League Baseball scandal. But anyway, so this is just a brief historical background. Now, back to more relevant stuff. So this is an incomplete list of steroids that as an analytical chemist, let's say involved in sports medicine, just think for a second of yourself working for an agency that deals with doping issue in sports. So this is a list of steroids that you might be dealing with in your analysis. And so one thing that immediately becomes obvious when you look at the structures closely is that quite a few of these structures are, and of course, this is an incomplete list. So there are isomers. And isomers, unfortunately, by the very definition, you have, Sadia, I think you need to mute, thank you. So for isomers, even if you use absolutely highest possible resolution, you would not be able to make a distinction between the two species based on their mass alone, simply because the masses are identical. The empirical formulas are identical, and therefore the masses are identical. And so in this case, you have to look at something else, some other ways to deal with this complexity. So the way you can attain selectivity in this particular case, as I mentioned earlier, you are looking at a chemical reaction. So you would select your ion of interest. You introduce some reaction in the gas phase. Usually the easiest thing to do is to have fragmentation in the gas phase. I'm sorry, somebody's not muted and we get feedback every now and then. Thank you. Okay, I cannot see who is not muted. Let me take a look. Aniket, I think it's you. Thank you.
Yeah, I am muted.
So, and fragmentation in the gas phase would be the easiest way to introduce a chemical reaction, and then we would need to look at the products, and the idea here would be to identify a unique pair of a reactant and a product that would be unique for one particular analyte. And if you can detect that, if you can use your instrument in such a way that it would be detecting just this reaction, then you would be able to attain the desired level of selectivity. So this is how it's done. So on this diagram, you see a tandem mass spectrum. So these are fragment ions that are derived from the protonated molecular ion of propyl trenbolone. So as you can see, this is one of my isomers that I showed before. And you see a really wide range of fragments. And so your hope is that if you look at fragments that are derived from isomeric species, you would be able to find one that is unique to propyl trenbolone. Okay, so you have to find some uniqueness. And so in our particular case, since we were only concerned with one other species, this is shown at the top of the diagram. So you can see that there are some opportunities for you to select unique ions, and in particular 227, so this fragment ion. At this point, we're not even really interested in what this fragment represents. All we need to know is that it is the product of this precursor of the molecular ion of propyl trenbolone, and it is unique to propyl trenbolone. So it is not produced by the isomeric species, right? There are a few other ions that would fit this criterion, but 227 is a good one because it definitely has highest abundance. So in addition to selectivity, we would also have decent levels of sensitivity. That's another concern that we always have to keep in mind. And so this is what you do. This is your a flow chart of your experiment. So listed here are molecular ions of all of the steroids that I had in my initial diagram. So these are the masses. And I intentionally round them to the nearest integer just to emphasize that we're dealing with very low resolution, right? This is by no means high resolution measurements. We do it with a quadrupole instrument. And there are at least two pairs of isomers here. So the pair that we're interested in is tetrahydrogestrinone and propyl trenbolone. Now, what we do to enable this type of highly selective analysis, we use a triple quadrupole instrument. Again, this would be my quadrupole 1. This is Q2, and this is quadrupole 3. So Q2 is just radio frequency on the quadrupole. I'm only using it for fragmentation. It does not have any discriminatory abilities, right? I can only discriminate among ions of different M/Z ratios using Q1 and Q3. So, and this is exactly what I do. So, oops, I'm going in the wrong direction. With Q1, I'm introducing all ions, all possible ions that can be produced by this mixture of steroids. And I set it in such a way that only ions at MOZ 313 are transmitted. So everything else would be lost here, right? So this is the arrow shown in maroon in my diagram. So I'm not scanning this instrument; it's fixed, right? So this is like a precursor ion mode. So I'm selecting only the ion of the MOZ value that corresponds to my analyte. It's not unique. Again, I have isomeric species, but this is what I do at this stage. And then at Q2, I introduce the fragmentation reactions, right? So we have collision gas, and we produce fragment ions, which I show in green and purple here, in addition to some surviving precursor ions, and they all move into Q3. And Q3 now, I'm not scanning this quadrupole. I'm setting it at a particular MOVZ value. And I am selecting 227. So this is the very same fragment ion that we discussed in the previous diagram. It's unique to propyl trenbolone, right? So it's produced from 313 of propyl trenbolone, but its isomer does not produce it. And so this is what we do. So again, I'm using the discriminatory abilities of this quadrupole, and only 227 is transmitted. And so what happens now, even though more than one steroid has this molecular ion, 313, and more than one steroid can give rise to 227, there is only one unique structure that would have them both. So it would have a molecular ion at 313 and a fragment ion at 227, right? So this is what I do. So I'm using the uniqueness of this reaction. So this transition from 313 to 227 is what allows me to gain this really high selectivity in this particular case. Okay. So this is an extremely useful approach to detection that allows you to achieve very high degree selectivity without having to rely on high resolution. And even I would again go beyond that, looking at the specific example that we considered here. You are really you can go beyond the capabilities that are offered by high resolution instruments, because in this case you can clearly deal with isomeric species. All right, so now let's move forward. If you have high resolution instrumentation, of course, and you have a capability to fragment your ions, then you can combine the best of both worlds, right? So you can do identification based on empirical formula, which you would deduce from the exact masses, and at the same time, you should be able to deal with fragmentation patterns that would allow you to establish uniqueness of isomeric species that may have that have this exactly the same mass, but their fragmentation patterns would be different. Okay, and so in modern high-resolution instruments offer this capability. So I just decided to show one example. This is still not quantitation, but you can think of that as a detection and identification type of measurement, which gets really, really close to quantitation, but not quite there. And so here you're looking at the ethanol extract of low molecular weight metabolites from human plasma. And mostly we are interested in lipids. So some of you probably recognize this chromatogram. So this is what was in your homework number 2, right? The chromatogram at the top is the so-called total ion chromatogram. So it shows the ionic signal as a function of the elution time. And of course, the beauty of mass spectrometry is that it allows you to look at each time point and identify species that are present there simply by looking, in this case, not just MS1 spectrum. So let's take a look at this. Let's say we're interested in this particular time point, right? So the spectrum shown at the top in the blue is MS1. So you clearly see molecular ion, and from that, by measuring it with high resolution, you can determine the empirical formula. Empirical formula in this case would be highly complex. So there would be dozens and dozens of species that would fit the same empirical formula. And in order to identify it completely, you would have to add another dimension. And this dimension is MSMS. So you do ion fragmentation on the fly. So it sounds very sophisticated, but fortunately, modern mass spec instrumentation allows you to do that. And in most cases, it's done without your involvement. So the instrument is typically set up in such a way that it can acquire mass spectra very quickly. And so what's done at certain time point, it acquires MS1. So it looks at ions without inducing any fragmentation. And then it automatically determines the highest abundance ion in the spectrum. And so in this case, of course, it would be this 496. And then in the next scan, computer tells itself to obtain a fragmentation spectrum of this ion using it as a precursor. So it would mass select it, introduce it into collision cell, introduce collision gas, induce fragmentation, and then it would collect the mass spectrum of all fragments. And in this case, it's not really you don't see a lot of fragments, so it's only the most abundant peak is 184. But in this case, it's enough for you to identify this compound based on database entries. So there are two major databases. One is maintained in Canada. One is made by Scripps Institute. So they're pretty much the same in their capabilities. I think the Scripps one is a little easier to use in terms of automation, but unfortunately you have to pay for that. So it's a subscription-based use. The one maintained by Canada, I will share some links with you later. I should have done it on this slide, but I forgot to include it here. So it's free to use, but it's a little more awkward, in my opinion, to use it in terms of automation. But both are fine. And so when you, in this case, I was actually relying on the database maintained on the Canadian database. And so it immediately allows you to identify, make unique identification of your compound based on both molecular ion and the fragmentation pattern. And so I show the results here on the right-hand side of this diagram. So this is one thing I want to emphasize, and I want to be impartial here. So obviously mass spectrometry is my profession and my passion. And, you know, I always find myself, you know, being a very vocal advocate of mass spectrometry. But I think in this case, I can give you an unbiased opinion that this is the most sensitive and the most universal way of detecting the widest variety of analytes that are of interest to biochemistry, biology, medicine, clinical chemistry, and so forth. And just to show you, since I have this diagram here, just to show you how sensitive this technique is, I want to bring your attention to this little pig. So this is something, again, this is the analysis that was done here at UMass. It actually represents, this is a blood from a lung cancer patient. And so when this analysis was done, of course, we see this great variety of lipids, which makes a lot of sense. These are known to be a major component of human metabolome as present in the blood. But this thing, when you acquire a mass spectrum, look at the exact mass, so which we can measure again with high confidence. And then you can also, what you can also do on the fly, you can fragment it. So the black trace on panel B shows the MSMS spectrum of this compound. And so when you try to match this data with the database, this is what you get, right? And this is interesting because this is an anesthetic, right? And so it was puzzling, why do you see a local anesthetic? The name is bupivacaine. So why do you see it in blood? And it turns out, after consultation with the physicians who obtained this blood sample, it was realized that the patient, in addition to drawing the blood, he had lung biopsy done, right? And when the biopsy was done, so it's done with the use of local anesthetics. And so this is exactly what had been used in that particular case during that procedure. A very small fraction of that got into the bloodstream. And so when the blood was subsequently drawn and analyzed, you could detect that. So this is really, really very sensitive method of analysis. And again, one thing I want to emphasize, you're not just looking at one particular analyte. You don't restrict yourself in that way. You can look at a great variety of things simultaneously. So in a single experiment, you are looking at a very large variety of analytes that are present in the blood, and you can, of course, it takes a lot of time to process the data, especially if you're not doing it. Well, I think right now it's probably impossible to do it without the use of databases. But usually in mass spectrometry, the data acquisition is not as challenging as data processing, perhaps, and analysis and making conclusions. So that requires a lot of input, a lot of effort. And suffice it to say that just the data set alone, a typical data set could exceed 1 gigabyte, right? Because if you think about that, you are acquiring data in 3 dimensions. So one dimension would be the elution time, that's your chromatography. The second dimension would be MS1. So these are the masses that are measured with very high precision and accuracy, masses of molecular ions. And the third dimension would be the fragmentation data. So this is what allows you to ultimately make all these assignments. So really, really wonderful technique. Again, in this class, we simply don't have time to go through all the capabilities that are offered by mass spectrometry. I apologize for being redundant. I think I said that several times already, but my colleague is going to offer a biological mass spectrometry class in the spring semester. 2024. So those of you who are thinking of using mass spec on more or less routine basis, I highly recommend this class. So this is something that you definitely need to do. All right. So going back to the slide, the only thing that you don't see here is the quantitation. So I said we see this all these lipids, we see anesthetics, we see a variety of other metabolites, but we cannot really say at what quantity they are present in the sample. right? And that's a very, very important characteristic when you do clinical analysis. And so unfortunately, in mass spectrometry, when you look at just signal intensity, that could be frequently very misleading, right? And so I put some of my considerations here on this slide. So one thing that you need to keep in mind that the signal intensity depends on a great number of parameters. Okay, and just simply by changing experimental conditions, or sometimes just making your measurements on a different day a week, you would have different results in terms of the intensity of the ionic signal. And so therefore, I think you can say, you can make semi-quantitative conclusions. You can say this is not very abundant or this is very abundant analyte, but you cannot really attach a specific number to this conclusion when you're looking only at the intensity of your ionic signal. And so therefore, the way we solve this problem is pretty much classical in analytical chemistry, right? We have to use internal standards. So internal standards are compounds that should have very similar, almost identical physical and chemical characteristics to your to those of your analyte. And at the same time, they should be distinguishable from your analyte in terms of the mass spec measurement, right? And so I want to show you a few examples of how this can be done in biochemical analysis. And I will start with a simple amino acid. Well, maybe it's not a simple amino acid, but it's a relatively simple organic compound. So this is levothyroxine. This is a very important hormone. Used as a drug for treating hypothyroidism. And so if you look here, so essentially this is just a modified tyrosine, right? Extended tyrosine and iodinated tyrosine. So the way to approach the creation and use of internal standards in mass spectrometry is to use isotopes. So this is the easiest way and the most probably the best way to make sure that your compound would have the same characteristics as your analyte. So in this particular case, it is possible to create an isotopically labeled species of levothyroxine by using carbon-13 isotopes for this ring, as I highlighted on my diagram. Right, so if you introduce this 6 carbon-13 atoms, then you would create a compound that would be chemically identical to levothyroxine. But now, all of a sudden, its mass has increased by 6 mass units, right? And so that would make it distinguishable from intact levothyroxine in your mass spectra. And so here we're looking at the negative ion electrospray mass spectra of levothyroxine spiked with a known amount of this internal standard. So my unknown levothyroxine is shown in red, and in blue is the isotopically labeled levothyroxine. So what I want to emphasize here on this slide, if you look at the ratio of the two peaks here, so we have two groups of peaks. Here the ions are produced by deprotonation. Here you use a very different mechanism. So instead of deprotonation, you actually attach ubiquitous chloride anion and you make the negative ion that way. So in the ions of the first group, if you look at the ratio of intact levothyroxine, unknown levothyroxine, and the internal standard, it's 1.16, right? If you look at the second group, it's again 1.16, right? So this is what I want to emphasize. Very different mechanisms of ion production, but the ratio of the unknown to the internal standard is the same, to at least 3 significant figures as shown here. So this is really wonderful. It also means that if I had some very sophisticated sample prep scheme prior to mass spec, so let's say I had to extract it from human blood and so forth, and inevitably I would have losses of my analyte, but this loss would affect both the unknown and the internal standard in exactly the same way. And so I would still maintain this ratio 1.16. Okay, so the losses would affect sensitivity, but they would not affect the precision or accuracy of my measurement. So this is a great thing, and this is what is used universally in mass spectrometry in various ways, and we're going to go through them in some at some level of detail in the remaining 20 minutes of the class. But this is the general approach. So you make a compound that has isotopic labels, and that changes the mass, but it does not change the chemistry or the physical characteristics of your molecule. All right. So the devil is in detail, though. It's very easy to make an isotopically labeled internal standard for a small molecule, such as an amino acid, but it's much, much more difficult to make it for, let's say, protein. And frequently in bioanalysis, what we have to deal with is quantitation of various proteins, right? And you might be interested in endogenous proteins that are present, let's say, in human plasma or in some bacterial cultures or in animal tissues, as shown in this diagram. Or you might be interested in, let's say, if you are working in the biopharma industry, so you're dealing with pharmacokinetics, so you need to know how the concentration of your therapeutic protein changes over time following the injection. And in all of those cases, you have to do quantitation of the protein, right? And that is an incredibly difficult task because usually just protein detection at the whole protein level might be challenging. The easier way and the better way to approach this problem is to employ proteolytic processing. So use some enzyme, let's say trypsin, and you would cleave your protein into pieces. Of course, if you deal with a very complex matrix, you're going to proteolyze everything that is present there, right? But the idea here is that you would create a large variety of proteolytic fragments. Some of these proteolytic fragments would be derived from your protein of interest, and then you quantitate your protein based on the abundance of these proteolytic fragments, right? So so here you would still use this approach, SIL. So this acronym stands for stable isotope labeling. So with that, we want to emphasize that we're not dealing with radioisotopes in this quantitation work, as has been done in early days, right? So we are dealing only with stable isotopes. We only the only thing that we want to see is the mass shift. And so there are various ways to introduce your internal standard, and depending on how you do it, that would have a very significant effect on the quality of your measurement, right? So in the ideal case, you would introduce your labeled intact protein into the unprocessed sample, and then both isotopically labeled protein, your internal standard, and the protein of interest, your analyte, would go through exactly the same steps in terms of extraction and fractionation, reduction, proteolysis, and finally they would be subjected to MSMS analysis, right? And so this is probably the best way of doing this work, simply because you by following all these steps, you ensure that all processes that may affect the abundance of the proteolytic peptide that reports the quantity of your analyte protein. So all of these processes would affect both the analyte and the internal standard in exactly the same way. right? So the problem with this approach, so this is the most accurate way of doing things. The problem is it's incredibly difficult to produce isotopically labeled protein, particularly if you deal with mammalian proteins, right? You have to use labeled amino acids, and it is not impossible, but it's expensive. And so usually it is so expensive that usually even biopharmaceutical companies prefer not to do that, even though usually they don't have cash limitations that are typical of academic labs. So it's just very expensive. And then what you would do, you would try to cut corners. So you can introduce your internal standard later. And the cheapest way, but this is also the way that most prone to introduction of experimental errors, is to introduce to use peptide standard and to introduce it at the very last step. So you already have proteolytic peptide mixture, right? So your analyte is here, and then you introduce your internal standard at this stage. So that's the easiest, the most economical way of doing things. The problem here is that you all the losses that occur here, they would not be reflected in your quantitation work, right? So your quantitation work will reflect the quantity of your analyte at this stage, but it may be different from what you had initially, right? You're not accounting for all the losses. But nonetheless, so these are two very different approaches to this problem. So this is the most accurate, but also the most expensive and most labor intensive. This is most error prone, but at the same time, it's least expensive and the easiest to carry out. And so I want to show you a few examples how this is done. So in this particular case, we are looking at quantitation of one of the therapeutic monoclonal antibodies, rituximab. And the quantitation in this case is based on tryptic peptides. So you have your entire sample. Since this is MAB, you probably take a blood sample. You extract proteins, you subject them to proteolytic fragmentation. In this case, it's trypsin. And so this is one of the tryptic fragments which you want to use for quantitation. So the sequence is shown in blue. It's derived from your analyte protein. So the way you would introduce internal standard here, you would introduce this peptide. And so this peptide, you would notice two things here. So first of all, this lysine is labeled. So you introduce 6 carbon-13 atoms and 2 nitrogen-15 atoms. So that shifts the mass by 8 mass units. And at the same time, you also extend the sequence of this tryptic peptide a little further. So you introduce a couple of amino acids on this end, or rather 3 amino acids and 3 amino acids on the N-terminal end. And so the reason this is it's done, even though you're dealing with peptide, but you call it pre-proteolytic peptide, right? So you would introduce it to the mixture prior to proteolytic treatment. And so here, at least you would account for some losses, for some incomplete proteolysis that may occur under your particular conditions, right? And so that would make your analysis a bit more accurate. So of course, in the ideal case, you would want to introduce the labeled protein, but labeled protein would have to, it would be impossible to introduce label in just one specific place, right? So this peptide can be produced synthetically, just using solid state synthesis. So that's relatively inexpensive. And at the same time, you still say, okay, it would still be subjected to proteolysis, right? So I would have to remove this tripeptide from the C terminus and tripeptide from the N terminus. So if my tryptic digestion is not ideal, my internal standard would be affected as well, right? And so the actual measurements that you would be doing on this sequence shown in red, right? So, there are two approaches shown here. At the top, you use high resolution mass spectrometry, just LC-MS, and you tune your mass spec just to detect these two signals. So these are the doubly charged species of these two peptides. Again, the mass difference is 8. That's due to these isotopes that you have in the internal standard. So one thing that you would see here is that the signal to noise does not seem perfect, even though you use high resolution mass spec. And the reason for that is in this very complex sample, so this is a tryptic digestion of all proteins extracted from human blood, right? And so there is a good chance that there would be other species having very different sequences, but their M/Z values would be very, very close to these two, what you're measuring, right? And that would create all these spikes in the background. So this is your chemical noise. And the diagram shown at the bottom, once again, demonstrates the power of the approach that we discussed in the beginning of today's class, use of triple quadruple instruments. So here, you are looking not at ions of particular mass, but at a specific reaction taking place in the gas phase, fragmentation reaction. So here you're looking at transition of precursor to Y11. So Y11, as you recall from last week, that would be the C-terminal fragment representing the last 11 residues in the sequence, right? And so because the labeled lysine is the C-terminal, at the C-terminal position, so both, I should put a star here, so both red and blue Y11 fragments would have different masses as well. And so these are the two transitions that you're looking now, and you see that by switching from monitoring masses alone to monitoring chemical reactions, you increase the selectivity very, very significantly, right? And so the chemical noise now, I think it's safe to say that it's reduced by at least an order of magnitude. So this is a very, very powerful approach. All right. So, but in many cases, just looking at the mass alone would be sufficient. And so here I want to show another example of quantitation of a monoclonal antibody. So in this case, the company who did this work actually went through the pains of introducing isotopically labeled analog of the monoclonal antibody, which then it used as internal standard in all this bioanalysis. And so here, let me just remind you the structure of the antibody. So the lyse-C, limited lyse-C digestion removes the FAB region. So this would be the FAB region of the antibody. And so here you're looking at relatively high mass ions. See, it's the mass is almost 50 kilodalton, right? But because it's limited digestion, the beauty of this approach is that you have very few proteolytic fragments. And so now you can have a relatively clean mass spectra. So the diagrams that you see on the left-hand side, the mass spectra have been deconvoluted already. So you see only masses. And so these mass would represent, the low mass would represent your analyte, the high mass would represent the isotopically labeled species. And as you can see, the the abundance of the labeled species, that's your internal standard, remains pretty much the same. So it's around 2,000 counts across the entire range of measurements. But the unlabeled species you analyze begins to decrease. And so this is how you would do pharmacokinetic studies. So based on that, and knowing the exact amount of the internal standard that you added to each sample, and in this case, I believe it was the same amount spiked into each sample. Now you can make kinetic plots and determine how the concentration of your protein therapeutic decreases in the blood as a function of time following the injection. Okay, so a very straightforward way of making these measurements, and perhaps a unique one. So it would be very, very difficult for me to think of any other method that would allow you to attain the same level of accuracy in your measurements. One comment that I want to make in the remaining 5 minutes of today's class is that the example that we have seen in the previous slide shows the internal standard that was made by essentially producing an isotopically labeled antibody. So that's an expensive project, right? And in many cases, it's not feasible. Other examples that we've seen are production of production of internal standards using synthetic methods. So one thing that lies in between these two extremes is the use of biochemical methods of producing the internal standard. And a very popular approach to this problem is illustrated in this slide. And so it's using a really interesting phenomenon, which I'm not sure if many of you guys are aware of, but if you have if you do proteolysis in heavy water, and heavy water means that it's not deuterated water, it's water that has oxygen 18 there. So what it does, it would introduce the oxygen 18 label into the carboxylic acid at the C-terminus. And if you have some other carboxylic acids, let's say aspartic acid or glutamic acid residues, it would also introduce oxygen 18 in those carboxylates, which is a wonderful thing because that gives you a relatively easy way to introduce isotopic label into your proteolytic fragments without the need for generating starting with the isotopically labeled protein, right? So this is a really useful thing. And so this is illustrated schematically on this slide. So you would start with your sample. So perhaps you go through some purification step, and you would do proteolysis as usual under normal conditions, as you typically do using normal water. Just to produce proteolytic fragments that would be used as reporters of the abundance of the intact protein. And at the same time, in parallel, you do an experiment under identical conditions, but here you start with a sample where you know exactly how much of this protein you have. So this would be your internal standard, but at this stage, your internal standard is not isotopically labeled. Okay, so you go through the same purification step, and then when you do proteolysis, you carry out it in heavy water. So this is water with oxygen 18 isotope, and that would introduce these isotopic labels. Then you would mix your samples together. So again, the blue sample, that's your unknown. So you know what your protein target is, but you don't know how much of it is there. And in the red sample, you have the known amount of this protein, and now it's isotopically labeled. So this is your internal standard. And so a typical spectrum is shown here. So in this case, we have 3 carboxylates, right? 2 side chains and 1 C-terminal. And that results in a mass shift of 12 daltons. So that's very, very significant. So that's enough to make a distinction between the two peptides, even though you clearly have incomplete incorporation of oxygen 18 here. So this is not 100% labeled. Again, this is not a big deal. You can take care of that during the quantitation step by accounting for these isotopes as well. But the wonderful thing is that if you look at the extracted ion chromatograms, so these blue and red peaks represent the elution profiles of these two peptides. They are identical, so they show up at the same time in your chromatogram, right? And so therefore, you don't have any effect of, let's say, variation of the mobile phase composition that certainly has effect on the intensity of ions you produce in electrospray and so forth. So all physical and chemical characteristics of these two ions are identical or nearly identical. The only reason, the only difference is the mass. And that's what allows you to make a distinction between them and then quantitation based on that. So a very useful tool, very popular both in academia and in industry. So this is called oxygen 18 labeling. And so with that, I think we came to the end of this class period. So I will finish my presentation and stay here for a couple more minutes if you have questions.